So we are on the topic of rationalizing substitution. I hope you can see my slide now. And we have covered the first two methods. As a review, the first one is applicable for an integral containing an nth root of an expression of ax plus b. So a is any constant, you have the x variable, and added to it is the other constant b. So whenever your integral is written in this form, it contains an nth root of the expression ax plus b. The first thing that you need to do is you have to assign a new variable to this nth root expression, then eliminate the nth root by raising the substitution equation to an exponent or power which is the reciprocal of your nth root. That way you get rid of the nth root expression. Okay? And the rest is you have to substitute the new variable to the nth root expression, and correspondingly you are to change the derivative of the original variable to the derivative of your new variable. Okay, so that's for method 1. For method 2, it's for those integrals that contains a mix of nth roots. Okay, you have here nth root of x, and this one is nth root of x. So these nth roots are not equal. So what we have to do is we're going to multiply these nth roots, yielding a new variable raised to a power which consists of the product of the exponents of our original variables in here. So in the case of this example, we have it 1/6 because you have here 1/2 for the square root, and we have 1/3 here for the cube root. The same procedure follows. So you have to assign a new variable to your original variable and then eliminate the nth root, and correspondingly substitute the new variable to your original variable in your integral, and you have to change as well the original derivative of the original variable to the derivative of the new variable. Okay, so in that case, that's done in here. Your dx is changed to the derivative of 6u raised to 5 du, the derivative of u raised to 6. Now, I think that's where we ended last meeting. So that's our short review. Is that right? For this afternoon, we're going to do trigonometric substitution. Can I have a reaction if this is correct, that this is where I'm going to start this afternoon on trigonometric substitution? Are you there, class? Or you...
Yes, I think so. Yes.
We are to
Yes,
we are to continue on trigonometric substitutions. I haven't started on this again. Okay, thank you for that. So this slide, actually, your second to the last slide, is all about substitution. So the first two methods is on rationalizing substitution. You need to eliminate the nth root expressions in the original integral. Now for this one, though this is applicable to the expressions that are only shown in here, you can use this trigonometric substitution whenever these expressions are present in your integral. So what are these expressions? So very limiting in the sense that you can only use this for this particular expression. So one expression is you have a real number, that's the a squared here. You subtract from it the square of u. U is, of course, like x or y. So any variable that is being squared. Now in here, you are to use the substitution equation u, whatever is your u here. If it's x squared, so this would be x. X is equal to the square root of the real number that you have here. So your real number is represented as a squared. So whatever is the square root of that, that would be a. And then you multiply it with the sign of theta. So you will use this substitution equation whenever this particular group of terms or this expression exists in your integral. Okay? Now, if we interchange the manner of subtraction, like we first have the variable that is squared minus a real number, a squared here, the substitution equation is changed by simply changing the sign of theta to secant of theta if you have interchanged these two. Now, if it's plus, so since it's plus, it doesn't matter whether you have u squared plus a squared or a squared plus u squared. So it doesn't matter because we know that in addition, the order is not important. So your substitution equation should be u equal to a tangent of theta. Again, I will emphasize that this is only limited to the expressions that you are seeing here. Okay, so if the integral that is given you does not contain this expression, then this particular substitution equations are not applicable. So only on cases where it is applicable. Okay, so let's go to specific examples on this, on trigonometric substitution. So let me go to the first example here. Now you're given the square root of 4 minus x squared dx. So in terms of form, class, okay, allow me to annotate. In terms of form, you have the 4 here as the a squared and the x here as the u squared. Okay, let me first change the size of the font. So your 4 here is the real number a squared, and your x here is your u squared. Okay? So if that is the case, if this is the form, then if you take the square root of the 4, that would be 2, so that is your a. You see here that your a is 2. Your x squared is comparable to u squared, so your u is equal to x. And it is to use the substitution equation. U is equal to a sine theta. What is the a? That's the 2. So you see here a 2, and then you just affix the sine of theta. Your u is x, so you place x is equal to 2 sine of theta. Now, this x that you see here in your original equation will then be afterwards replaced. It will be replaced by 2 sine of theta, the x that you have here. Now, in the same way that you have changed the x in terms of the new variable u, or rather in terms of the new variable theta rather, then there's also a need for you to change your dx to the variable of theta also. So it should not be dx, but it should be d theta. So what do you do? With this substitution equation, this is your substitution equation that will replace the x squared in here. You differentiate the substitution equation. So this will give you a dx on the left side. 2 is a constant, and it is to be multiplied to the derivative of the sine of theta. So the derivative of sine theta is cosine of theta. Now these two expressions that I have underlined should replace the original x squared and dx here in the integral that is given to you. So look what happens here. So you have square root of 4 minus. So your x is 2 sine theta. But since this is squared, so you have to square this also. So you see 4 sine of theta squared. The dx should be replaced by an expression in terms of d theta. And that is 2 cosine theta d theta. Now this 4, the 4 that you see here inside the radical sign is actually factorable. So if you're going to factor that and get the square root, that would be 2. So that's the 2 that you see here. And what is left if you factor it out already is 1 minus sine squared theta. And we still copy the 2 cosine theta d theta here. Now, what is the equivalent identity of 1 minus sine squared theta? That is according to your trigonometry, cosine squared of theta. So you see here now, it's 2 square root of cosine squared theta. Again, we copy the 2 cosine of theta d theta. Now these 2 and these 2, if we multiply, that would be 4, and it's a constant, so it's written before your integral. Now the cosine squared of theta, when you take the square root of that, would be cosine theta. Multiplied to this cosine theta would be cosine squared theta d theta. Now this falls under trigonometric transformation. The square of a cosine or sine, or a cosine or a sine raised to a positive even exponent, will be converted first or transformed first to its equivalent identity in terms of the double angle cosine. So your cosine squared theta is actually equal to 1 plus cosine 2 theta divided by 2. Okay, that is its equivalent identity. So we can replace this one. That way we can integrate this one easily. Now the 4 here will cancel one of the 2's here, leaving you with a 2 in here for the 4. So it's now 2 multiplied to the integral of 1 plus cosine 2 theta d theta. Now, for the first part, you have 2 integral of d theta. For the second part, you have 2 cosine 2 theta d theta. Now, these 2, you can place again back in here because the u is 2 theta and the du of that is 2 d theta. So if you're going to use the 2 in here and place it after your integral to represent the derivative of the u, then you can now write the integral of the cosine of 2 theta, which is the sine of 2 theta. So this is now your answer. The answer for the integral of d theta is theta. So you multiply it by 2. And the answer for the cosine of 2 theta is sine 2 theta. Now, ever wonder why it's written here as 2 sine theta cosine theta? It's because your sine 2 theta has this equivalent identity of 2 sine theta cosine theta. Now, that's an identity that you've learned even starting junior high. Okay? Now, if you look very closely to our answer class, if you look closely to the answer, it's in terms of theta. Your original integral is in terms of x. So how are we going to return, or how are we going to express our final answer here in terms of the x variable that is present in your original integral? Okay, the answer is you have to construct a triangle. You have to construct a triangle, I will emphasize, based on the, I'll eliminate the markings, based on this substitution equation. You construct a triangle. I write triangle specifically based on the substitution equation. What will I get from the substitution equation? From that, I'll be able to get that x divided by 2 is equal to the sine of theta. And place the 2 below. So x divided by 2 is equal to the sine theta. How am I going to use this? Remember in your high school that the sine of theta is equal to the length of the opposite side of the angle theta divided by the length of the hypotenuse. So this x and this 2 represents the opposite side and the hypotenuse of the right triangle where theta is found. Okay, I will illustrate to you, or the next slide will describe to you how will we use the x over 2 equal to sine theta in our triangle. So it's here it is. You see this? Your theta is in here. So opposite side is x, hypotenuse is 2. Determining the side adjacent to theta will use Pythagorean theorem. So it's the square root of the length of the hypotenuse squared minus the length of this side squared. Okay? Now, I hope you now could grasp the importance why the sine 2 theta, that you see here as the original answer needs to be converted to sine theta cosine theta. It needs to be converted to this because we will get the sine of theta and the cosine theta from the triangle. From the triangle, we don't have the sine of 2 theta. We only have the sine of theta. So that's the reason why there's a need for you to convert this to its equivalent identity in here containing the sine and the cosine. So if I go back to the next page, you will be able to see that for 2 theta, so you have the 2 in here. What is theta? Remember that, let me annotate. Remember that the sine of theta is equal to x over 2. So how do we find theta? It's the arc sine of x over 2. So that's it. Theta is the arc sine of x over 2. And since it's multiplied by 2 in here, so you have it here. As for the 2 sine theta cosine theta, so 2 is copied. What is sine theta? It's x over 2. X opposite over the hypotenuse. Cosine theta is square root of 4 minus x squared over 2. Adjacent over the hypotenuse. Plus c. And then the rest is just simplifying the second term here. So you get to cancel the 2's. And you still have another 2 in here. So that is why you have 1/2. And then this x square root of 4 minus x squared plus c. Do you get it, class? Do you understand the solution? So this one now, this one is the solution of the original integral in terms of the variable x. We don't stop on the answer that is in terms of theta. But rather, we constructed a triangle using the substitution equation and make sure that our answer is in terms of the original integral in terms of x. Now, do you have any questions? No
None,
questions?
miss.
None? Okay. We'll clear the markings and we'll go to the second example. Now, we have this integral. So it's not only limited to nth root like 1/2, 1/3, 1/4. It could even be in the square root in this particular exponent. Okay, 3/2. So your expression here, 1 plus 36x squared, if written under the radical sign, would be raised to 3 and then under the square root sign. So that's it. So it's still representing the nth root of an expression. What expression is that? Speaking of the expression, this is comparable to a squared and this is u squared. Okay, looking at it, if a squared is 1, it follows that a is 1. Looking at it that u squared is 36x squared, then u must be 6x. So you see it here? The u, which is 6x, is equated to a, which is 1, tangent of theta. Because for a squared plus u squared, it's u equal to a tangent of theta. So this is our representation now. And this is your substitution equation. So you can simplify this or simply simplify it mentally, and when you substitute, that's the time that you correctly substitute the x or the square of it. But after you have written the substitution equation, just like what we have done in the first example, there's a need for you to differentiate this. That way, the dx here in the original integral will be changed to d theta, or in terms of d theta. So you differentiate this one, it's 6 dx, and you differentiate the tangent of theta, that's the second squared of theta, d theta. Okay? So this will be your substitution equation. So these are the expressions you will get, the dx and dx. Now, if we go back to our original integral, you have 1. The denominator is 1 plus, what is this? 36x squared. If you square this one, this will be 36x squared. Then you square this. That would be tangent squared theta. So you see here, tangent squared theta. And since it's raised here to 3/2, let me erase this one. Now, since it's raised here to 3/2, you also raise this one to 3/2. Now, your dx is to be taken from here. You just transfer the 6 in the denominator of second squared theta d theta. So that's the purpose you have this. This constant 1/6 is now written here before your integral. This 1 plus tangent squared theta is actually, in terms of identity, second squared of theta. It's raised to 3/2 here, so you raise it also to 3/2 here. Now, this will cancel the squared here and the 1/2 in here, meaning the second here in the denominator will be raised to 3. Okay? However, you have your second squared, so you cancel the entire second squared here and take 2 from this one. So that's the reason why you have here, this 1/6 is in here. So you have 1/6 integral of 1 over second theta d theta. What is 1 over second? That is cosine. What's the integral of the cosine? That's the sine. You get it? Now, the last part is, of course, we have to return the answer in terms of x. It has to be expressed in terms of x because your original integral is in terms of x. So where will you get the sides of the triangle you need to construct? It will be taken from 6x equal to tangent theta. From there, you can get that 6x divided by 1 is equal to the tangent of theta. What is tangent? Opposite over the adjacent side of the angle theta. So you use this as your guide when you construct your triangle. Okay? Questions?
Question.
Yes.
Where did we get the tan theta ganun, miss? So 6x is equal to tan.
Okay. It's taken from the substitution equation. The substitution equation, if you have the form, we have 3 substitution equation. One of the 3 is this, a squared plus u squared. Whenever you have this, you can use the substitution equation. If you have this, your u is equal to a tangent of theta. This is your substitution equation. If you have this expression. Now, this one is comparable to this. So your a squared is 1, and your u squared is this, the 36x squared. So from in here, you get to see that your u is 6x. So you place 6x. Because your u squared is 36x squared. So you get the square root of this, that would be your u. Your a is 1, so it's understood to be 1 in here, then tangent theta. This is the substitution equation you use whenever you have this expression in your integral. Did you get the explanation?
Yes, miss. Thank you.
Okay. Before I proceed, some more questions? Questions? None? Okay, then I will proceed if there are no questions. So our goal this time is to remember this is your answer, but this has to be expressed in terms of x. So we will construct the triangle with this as the tangent of theta, 6x over 1. We always construct our triangle based on the substitution equation. I will clear my markings here. And before I go to the next page, to the one who asked the question, maybe you came in late, these are the three possible expressions and their corresponding substitution, trigonometric substitutions. It's only applicable to this scenario. So if it's not the same to this one that is written, then you cannot use this one. The a squared here could be any real number, and the u could be x, any variable that is being squared. Okay? Now I'll go to the continuation of that particular example we have here, and we are now on the finishing part. So you have 1/6 sine theta. So based on our tangent, 6x over 1, if this is our theta in our triangle, opposite 6x, adjacent is 1. So the hypotenuse will constitute of the sum or the square root of the sum of the square of the sides. So you have 1 plus 36x squared, the square root of that for the hypotenuse. So if it's the sine that we are after, the sine is opposite over the hypotenuse. So you have it here. So this sine theta should be replaced by this, as you can see here. Now we can simplify further by taking out the 6. So you have simply x over the square root of 1 plus 36x squared plus c. This is already this is the answer. This one is the answer to the given integral. So the substitution equation we used here is the u equal to a tangent of theta. Before I go to the last, do you have any questions? Last example on this. Okay, there's none. Okay, then I will proceed if there are no questions. Okay, the last example is a different substitution. At this time, the expression that you see here is u squared minus a squared. So the opposite of sine. U equal to a sine theta. So the opposite is u a secant theta. So our substitution for this is u equal to a secant theta. Of course, you need to identify what is your u. So if it's 4x squared here, your u is 2x. What is your a? If your a squared is 9, it is 3. So you see here, u equal to 3, which is a secant theta. This substitution equation, just like our first two examples, should be differentiated. That way, the dx here will be replaced or can be replaced by its equivalent in theta or in d theta. So differentiating the left side, you have 2 dx. Differentiating the right side will have 3 because it's a constant, and it needs to be multiplied to the derivative of the second. What is the derivative of the second? Secant theta tangent theta d theta. Okay? Now this expression and this one will replace the original x and dx here in our integral. So you have 1. What is x? Because you have an x squared here. Your x from in here is 3 cosine of theta divided by 2. If you're going to square that, that would be 9 over 4 second squared of theta. Now, square root of, so what is 4x squared? If you're going to square 2x, that would be 4x squared. So then you must also square this one. That would be 9 second squared of theta minus 9. You just copy the 9. The dx will be this one. 3 second theta tangent theta d theta divided by 2. So we have this one now. Okay? Now, this 4, it's in the denominator, right? So it will go up here. So since you have a 2 here, it will cancel the 2 and you will be left with 2 in here. This 3 and this 9 will have the 3's canceled, leaving you with a 3. So the 2 that goes up divided by 3 is now written before your integral like this. It's now 2/3. Okay, it's now 2/3. Then you are left with second squared theta here. The square root of the square root of, this is already 9 second squared theta minus 9. You have 9 as something common. See, it's factored out in here and you write the quantity second squared theta minus 9. Okay, you just factored out the 9. Then copy the secant theta, tangent theta, d theta in here. Okay, let me just first admit your classmates. There you go. Okay, so we have this now. Now, you see this second squared and this second here, we cancel this. We take out 1. So, only 1 second left there. This 9 under the square root sign will be 3. So, it will be multiplied with this 3 here, giving you a 2 over 9. It's already in here, in the last part. So, you see a constant that is 2 over 9. The square root of 9, 1 over 9. The 1 over square root of 9 is 1/3 multiplied to 2/3. So, that would be 2 over 9. Your second squared theta minus 1 is actually tangent squared of theta. Okay? Identity. Tangent squared theta plus 1 is second squared. So, we'll just work around that particular identity. We can replace the second squared theta minus 1 here by tangent squared theta. Okay? Now, I took out the 1 in here. So, this would be left with 1. Now, this tangent squared under the square root sign will be tangent. So, it will cancel this one. So, what is left is the 1 over secant theta. 1 over secant theta, this 3 and this 3 were already multiplied in here, is cosine theta. D theta. The integral of that is sine of theta. So just like the second example, you will find what the sine of theta is from the constructed triangle. Where will you get the sides of the triangle from? In here. So second is hypotenuse over the adjacent. So 2x over 3 is equal to secant of theta. Hypotenuse over the adjacent, because secant is the reciprocal or inverse of the cosine. Now, before I go to the next page, the last page on this topic, you have any questions? Any part in here which you cannot follow? So, no questions? Now, I will clear the markings here so we can proceed to the last page. So, this is our answer from the previous page, to 2 over 9 sine theta. So, our goal is to find the sine of theta. We know that 2x over 3 is secant, so it's hypotenuse over the adjacent. So finding the side opposite theta will require the Pythagorean theorem again. So it would be the square root of the square of 2x, 4x squared, minus the square of 3, which is 9. Now, the sine of theta then will be the square root of 4x squared minus 9 divided by 2x. So your 2 over 9 this time will be multiplied to this because it's sine theta in here. Again, we cancel the 2. So you have 1 over 9 square root of 4x squared minus 9 over x plus c. Now, do we have any questions? Again, with the many formulas that you already learned, there is an important reason why you need to have a summary of formulas. You should have the notes. That way you can have easy access on that notes which you organize. It should be organized for you to use when the need arises. Now, question here. Okay. So we'll have a 10-minute break. Okay, my markings here. My time is 3:44. So let's say it's 3:45. You have a 10-minute break. Come back at 3:55. Okay, 10 minutes. 3:55, and we will start with the last topic on the method of partial fractions. That would be the last 4 techniques of integration. Okay? Okay, I'll give you your 10-minute break now. Okay, I hope you can see my slides now. We are on the method of partial fractions. If you'll not be able to finish this, I think it would not be finished. Then we will continue on Thursday. We still have Thursday. Okay? Now, the method of partial fractions, number 1, when you look at it, will automatically tell you, looking at the integral, it will automatically tell you that there is no other way, there's no other technique that I will use in this case because it is a fraction. Okay? It is a fraction, and the fraction has a polynomial. So I know you know what a polynomial is. It's a rational expression or a fraction wherein the numerator and the denominator, both of them, have polynomials. What do we mean with polynomials? Having several terms with variables x raised to a certain power together with constants. That's a polynomial. So when you are given a rational expression to integrate, or it's a fraction to integrate, wherein the numerator and a denominator are both polynomials, then you have to think that the method of partial fraction is the thing for you to use. Now, what would be then the process or the steps that you need to look into and use? That way you can solve that particular integral using the method of partial fractions. I will read the steps to you. It's in here. And I will again emphasize and mention the steps when we go to specific examples later as I proceed on the slides. Okay? So step 1, if you are already going to use the method of partial fraction, step 1 is you set up the partial fraction decomposition. Later, you will know what is this partial fraction decomposition. This partial fraction decomposition will have unknown constants. We refer to these unknown constants as unknown coefficients, A, B, C, etc. Etc. meaning class, it could have even a D, an E, or an F, depending on how many partial fractions you have in your decomposition, or how many partial fractions you have equivalent to the original given fraction. Okay? So you have to set up the partial fraction decompositions with the corresponding unknown constants A, B, C, etc. Now, after you have done that, the next step is you will multiply the equation which you have set up that includes the partial fraction decompositions by the least common denominator. The least common denominator is the denominator of your original fraction in the given integral. So your equation has to be multiplied to that. After doing that, you can now simplify the right side of your equation. Actually, you can simplify both sides of your equation now after you have done the multiplication process. After you have simplified, you write down the sides of your equation in descending powers of x. Let's say we're used to having variable x. So in descending powers of x. What do we mean by that, class? In our dialect, ang left side, ang wala kang tuo nga parte sa imo nga equation, i-arrange mo ang variables descending powers. What do we mean descending? Starting with the variable having the highest exponent down to the constant. So that's how you should arrange it. Both the left side and the right side of your equation. Why do that? Why arrange your variables in the sides of your equation in descending powers? Because in step 4, you will equate the coefficient, still on step 4, of the x cubed in the left side and on the right side, of the x squared in the left side and in the right side, and so on and so forth. You will equate coefficients. The purpose of equating the coefficients of these variables is to determine in step 5 the unknown constants or the unknown coefficients A, B, C. After you have done already the determination of the unknown constants, you can now substitute the values of the A, B, C in the original partial fraction decompositions that you have written and integrate each partial fraction separately. That's it. You integrate each partial fraction separately. Now, I will go back to these steps which I have read to you as I go along in the examples that is prepared in this set of slide. Now, study step number 1. You will encounter a lot of examples for integrals that are fractional in form, or rational in form, wherein since the numerator is a polynomial and the denominator is a polynomial, they are not simplified. What do I mean they are not simplified? They are not factored. So if they are not factored, you have to make sure that if possible lang you factor both the numerator and the denominator. That way, if there are common factors, you can have it canceled out, and that simplifies your given integral before you proceed to the process, the 6-step process. So, factor. Before you even factor, it's not written there in the study step, you make sure that your degree of the numerator is less than the degree of the denominator. Now, what do I mean with the degree of the numerator and the degree of the denominator? In your algebra, you've learned what we mean with the degree of the equation or the polynomial. The degree of the polynomial is the exponent, the highest exponent in which the variable of that polynomial is raised to. So you have to make sure even before you start factoring that the degree of the numerator is less than the degree of the denominator. If it's not less than the degree of the denominator, you have to resort first to long division. How do we do long division? That will also be illustrated to you. So the step, class, is this, if I will summarize. Inspect the degree of the numerator and the denominator. If the degree of the numerator and the denominator, if the degree of the numerator is equal to or higher than the degree of the denominator, divide first. Resort to long division. After that, after you have done the long division, it is really certain, class, that you will have a remainder in your division process. Just make sure that your remainder is already factored. I'm referring to the numerator and the denominator of your remainder. After you have done factoring, then you process it using the 6-step procedure that I have read to you a while ago. Now, if the degree of the numerator is less than that of the denominator, you can go straight to factoring because there's no need for you to resort to long division. Okay? Now, to illustrate what I mean with the processes I've mentioned, let's go to this particular example. Let's say this is the rational expression that is written in your integral. Okay, let me just place this on the side. So let's say this is your integral. You have a polynomial numerator and you have a polynomial denominator. The degree of the numerator is 3. The degree of the denominator is only 2. Since this is higher in degree than the denominator, you do long division. So this is the long division process. You copy the numerator, you copy the denominator, and divide. When you start dividing, I think this was taught to you in algebra, make sure that you have arranged also your terms in descending powers. Starting with the term with the highest exponent down to the constant. The same thing with your divisor. Okay, when you do long division, this is 2x cubed, you divide by x squared, so you lack 2x to make it 2x cubed. This 2x should be multiplied to the 3 terms here, and this is the answer. Then you subtract. After subtraction, you will have 5x minus 3. This is the one I'm referring to as the remainder. You cannot have this already divided by this because 5x is already of lesser degree than x squared. So the way we write now our integral after we have done long division would be this. It would be now the integral of 2x plus 5x minus 3 over x squared minus 2x minus 3 dx. So this is your integral now. The first term, of course, you can do power rule with this. You can answer this right away using power rule. The second term, you can't. This is where you're going to apply method of partial fractions. Now, notice that after I have done my long division, I did the long division here, I factored the denominator because it's possible for me to have it factored. The numerator, I cannot factor anymore, so it stays. Now, you may wonder why. What's the other reason why you need to factor the numerator and the denominator aside from simplifying your fraction? The purpose, class, of factoring, especially the denominator, is that you will properly write down the, shall we say, the decomposition of the partial fractions. These are the partial fractions equivalent to the original. Or shall I say this is the decomposition of the original fraction. So it's decomposed now to these partial fractions. Factoring the denominator allows you to know how to write properly the partial fraction equivalents of the original fraction. Looking at the factors, you will know how to write the partial fractions. These factors, we call these linear factors. Why I call linear factors? Because x are all raised to 1. So it is that of a line. It's comparable to an equation of a line, which is y equal to ax plus b. Okay, so it's linear. So if it's linear, then the way you write its partial fraction decomposition will will constitute two partial fractions in which the denominator are these linear factors. The denominator of your partial fractions are the linear factors. Now, question is, how about this 3 and 2, Miss? Where did you get this 3 and 2? These 3 and 2 are actually the A, the B, the C, etc. In this case, you only have until B. The A and the B, the unknown constants. How we determine this A and B, that will be illustrated in example number 1 on the next slide. Okay. Okay, it's okay. Hi. Now, any questions so far? So the process of doing the long division and factoring after the long division whenever possible is already illustrated here. Now we go to the actual application of the 6-step procedure. Okay? There are 3 types here in this slide which I will cover for the method of partial fractions. We will continue next meeting, of course, because this will not be all discussed now. Okay? Before I go to the next slide, do you have any questions? None? Okay, so we go to type 1. I think this is what we can cover for now. Type 1. You have linear factors. The linear factors that I'm referring to are the factors in the denominator. Okay, what do we do with linear factors? So this is the procedure of how we deal with linear factors. When the denominator of a rational expression contains the power of a linear factor or a power of a linear factor, set up the partial fraction decomposition with constants a, b, c, etc. When the denominator of the rational expression contains a power of a prime quadratic factor, set up the partial fraction decomposition with linear numerators. Your numerators this time are not simply a, b, c, but rather linear in nature. So one numerator is ax plus b, and one numerator can have cx plus d, and so on and so forth. When is this? When your denominator is a prime quadratic factor. That is type 3. The one that I'm going to discuss now is one which is the power of linear factor, or a power of a linear factor, wherein the numerators are just constants, unknown constants. Okay, so we'll use the first here. The second part will be for the third type. Okay, I will now clear my markings. Let's look at this example. Actually, this is the solution of this part here. This one. So we will solve the solution why we had 3 and 2. Okay, so you have that. 5x minus 3 over x squared minus 2x minus 3. So you have factored the denominator. This is now your decomposed partial fractions. The linear factors you have here are written in the denominator, and you write here your unknown constants. You can have this class interchange. You can even have the x plus 1 in the first, then x minus 3 on the second. Now, this is the first step. You write the decomposed partial fractions. So this is your decomposed partial fractions, equivalent to the original. Okay, that's the first step. The second step is you have to multiply. You multiply this decomposed partial fractions, which you have equated to the original, by the LCT. What is the LCT? Actually, you will simply have to multiply this by this one, x minus 3 and x minus 1, or rather plus 1, because it's the LCD. Okay, both of this side and of this side. In the process, what is left on the left side is 5x minus 3. And what you have here on the right side is a times quantity x plus 1 and b times the quantity x minus 3. Okay? You have already multiplied and simplified. That's step 2. Step 3, you simplify your equation. Simplify your equation. So this is 5x minus 3. You distribute. You also distribute. So you have this one now. Now, these are the unknown constants in the first place that we need to determine the value of. So we go to step 4. What is step 4? You equate the powers of x and the constants in the left side and in the right side of your equation. What does it, how do we translate that to doing in here? Or how do we translate that into something concrete in here in what we are doing? You will equate the term that has the x on the left side, so that's 5x, to the terms that have the x on the right side. So in here you have ax plus bx. If this is minus bx, this should also be minus. Then you divide the entire equation by x, so you just drop the x. Now you have an equation which is 5 equal to a plus b. You don't solve anything here because you have two unknowns. So this is your first equation. Now the second thing that you will equate are the constants. So in the left side you have minus 3, and on the right side you have a, and you have this negative b3 or 3b. Okay, they are all constants, and this is your equation 2. You have two equations with two unknowns a and b. Using your algebra, you can find the value of a and b. So solve two equations with two unknowns. Okay, that's already your step 5. Now we proceed to the next. What happens after that is this. You determine the value of the a, which is 3, and the value of the b, which is 2. After you have done a and b, or after you have determined a and b, you go back to your decomposed partial fractions and substitute the a, which is 3, and the b, which is 2. And you are now ready to have it integrated. Now, when you integrate this, it's just an ln. Why? Because this is your u, x minus 3, the du of that would simply be a dx. The same way with the x plus 1. The du of that would be just dx. So then you have an answer of 3 ln of x minus 3 plus 2 ln of x plus 1 plus c. And that's it. This is the answer of this particular integral. So if you're going to go back to our original example, you need to integrate this one, which will give you x squared only, because that would be 2x squared over 2. So this will give you an x squared, and the answer for this will be added to that. And that's the one that is shown to you in here. This one. So this is actually the method of partial fractions. Now, let me go back in this part here. Okay, I'd like to emphasize something. In here, you have only equated 5x, or variables, or terms rather, not variables, terms which has the x. If you have terms here which is x squared, you should start with the x squared. The same thing here on the right, you start equating x squared. You equate, or you make your equation starting with the variable having the highest exponent. For example, you have an x squared here, and you don't have an x squared on the right, then this side would simply be equated to 0. Because you don't have a term which has x squared on the other side. Okay? So you equate, actually we call it equating the coefficients of the powers of x and the constants. That way you find the unknowns. In this case, it's simple because you have only two unknowns. Now, in my third example, it's very long. That is why we'll keep that, we'll leave that for Thursday you will have 4 unknowns. So your algebra will really be tested in terms of finding the values of 4 unknowns using 4 equations. Okay? Now, there is an alternative class in equating coefficients. But this alternative is only applicable if your factors are linear, meaning x plus 1, x minus 2, x plus 5, x minus 25, something like that. If it's already x squared, this is also applicable, but it would still make the process long because you need to substitute it and you will not have any of the terms equated to 0. Now, what do I mean? I like to end with this alternative procedure. This is the shortcut method we call the Heaviside method. Now, you still set up your original fraction equated to the decomposed partial fractions. Then you still have to multiply it by the LCD. So you have this. Now, your key here is this equation, the simplified equation. Looking at the right side, wherein your unknown constants are multiplied to linear factors, you simply inspect what value of x you will place in here. That way, this term will be 0. Then the same thing with this. What value will you place in here for the x? That way, this term will be 0. The Heaviside method zeroes a particular term or terms based on the value of x that is used or substituted to the equation. So let's say we substitute x minus 1 here. So substitute here x minus 1. Do you have here negative 5? 5 minus negative 1 minus 3. So that would be negative 8. This one would be 0 because that would be negative 1 plus 1. This one becomes b times negative 4. So negative a is equated to negative 4b. b is already 2. Okay? Now, if you substitute 3, this will be 0. This becomes 4. And this becomes 15 minus 3. That would be 12. So you have 12 equated to 4a. You substitute 3 here. So a is 3. The reason why it's shortcut is really shortcut. You don't have to do elimination and substitution. You already find A and B. Just the same with the previous part, you substitute the value of the A and B that you got and integrate your expression. Okay, so substitute mo naman siya. Sorry. So that's it. And you have this one, and you substitute it in here, and you have this as the integral. Okay? So we have already done, you're done with type 1. That is your fraction is composed of a denominator consisting of linear factors. Type 2 is repeated linear factor and type 3 is prime quadratic factor, which we will discuss next meeting. Now, do you have any questions?
None, ma'am.
None? Okay, so I will just go over the attendance again. Now, although I already marked those that have informed me that they have connectivity issues. Excuse me.